Hello guys. All right, so here's my attempt at recording my lectures as if I am doing them in class. Again, this is my first time sort of doing this, so of course it's not going to be all perfect. So again, I'll just try to do as similarly as I would do in class. So just try to follow along, and of course, if you get stuck at any point or I'm going too fast, make sure to pause the video and to finish writing before you move along. Also, if you have any questions or you don't understand a concept or a step, make sure to make a note of that so that you can go ahead and ask me about it after you're finished watching the video. So yeah. All right, so we're going to start with chapter 8. Now, chapter 8 is sort of similar to chapter 7 in the sense that we are still looking at a probability distribution. So we're still going to be finding probabilities. And in the way that is similar to chapter 7 is that we are still going to be looking at a normal curve. What changes now is the variable itself. So if we look back at chapter 7, in chapter 7, we talked about some random variable that was continuous. Right? So for example, weight. And if weight follow a normal distribution, then we were able to find the probabilities for the normal variable using the normal curve, right? And so all we had to do is find the area under the normal curve, and to do that we used normal CDF, right? Where we had to specify the lower bound and then the upper bound, then the mean, then the standard deviation. So this gave us the probability or the area that x is maybe greater than or less than or greater than or equal to maybe, whatever number that may be. So here the emphasis was on the variable itself, right? Based on the normal distribution. The way that this changes in chapter 8 is that instead of looking at individuals or a whole proportion of the population, we are going to be looking at a sample, and from that sample we're going to have a mean, and so we call that x bar, right? And this x bar changes every time we select a new sample, and hence x bar becomes its own variable, just like weight would do for per person. Now we're looking at a mean of weights for a sample of people. So now the question is, what distribution does x have, right? What is the shape? What would be the mean? What would be the standard deviation and whatnot, right? So that's what we're going to discuss, the shape, the center, and spread, and also how we're going to be finding probabilities for it. So in the first section, we looked at the distribution for x bars. So the distribution for x bar is called a sampling distribution of the sample mean, right? So the sampling distribution, it just says that it is a distribution based of a lot of samples for which each sample we calculated a sample mean, right? So here's a way to illustrate what's going on. So let's say we have some distribution. Okay, so here we're considering the distribution for rolling a fair die, right? So here we have the different values of the variable, which in this case the face of the die, and the relative frequency, which ends up being the probability of each of those outcomes. Now the probability of rolling a 1 or a 2 or a 3 through 6 is the same probability, which is 1/6. Once we look at that in decimal form, it will be about 0.1667. All right, so since each outcome has the same probability of happening, once we graph it, now it looks like a uniform distribution, because for each outcome right down here, they have the same probability of happening, which is the about 0.1667. Right? So each face of the die is the value of x. Right? So we have a uniform distribution because of the shape that emerges from it. So based on this distribution, if we recall back from chapter 6.1, the way to find the mean is to look at the sum of the values of the variable times the probability of each. So if we do that here, we're going to get 3.5. And if we look at the standard deviation, we first had to find the variance. The variance was the sum of the x's minus the mean, square that times the probability of x, so that was the variance. But then we took this variance and we took the square root of that to find the standard deviation, right? So we call this one was sigma, and over here the mean was mu. And so if we do this for this problem, we're going to get about 1.708. So then the mean here ends up being right in the middle. And then the spread right here is based on 1.78. All right, so what we're going to do is we're going to take this distribution to roll in a die, and we're going to take samples. So that means we're going to roll the die more than once. So here's what we're going to do first. We're going to roll the die 4 times. And so you roll the die 4 times, and then you look at the faces of those 4 times that you roll it, and then you find the average of those 4 faces. Right? And then we do this 200 times. Okay? That means we're going to obtain 200 x bars, right? Because for each of these, we're going to calculate the sample mean for each of those 200 samples. So then you end up with 200 x bars. Once you take those 200 x bars based on the 4 rolls for each, and you graph these x bars, then you obtain this distribution. So notice that now the values here on the number line, these are x bars. So they're not individual values of the face. Now is the average of the 4 faces that we got from the sample of 4. If you were to calculate the mean of these, ends up being at about, let's see, for the ones I generated, I got a mean of those x bars to be about 3.49, which is really close to what the actual mean was of just the regular distribution. It was 3.5. The standard deviation for these x bars ended up being about 0.854. So if you look at the distribution, is no longer uniform, is more of this like almost approximately bell shape, right? Of course, you don't have that exact bell curve, but you know, it's starting to resemble that bell curve. If we were to then do the same process, but now we take a sample of 10, meaning now we roll the die 10 times, and for each of those 10 times we roll it, right, we denote the face and then find the average of those 10 faces, and we do this 200 times, then we obtain this distribution right here in this picture. So again, remember that the variable here is x bar, is the average of each of the 10 rolls, right? And so we get this shape now by rolling the die 10 times instead of 4. And if you notice now, the shape is a lot more bell shape. Right? If you were to find the mean also ends up being very close to 3.5, and the spread ends up being smaller, because now notice most of the values are within this range, right? So the spread and the standard deviations are being smaller. Let's look at the last one, so that we can see the final result. Now we're going to roll the die 30 times. So you re-roll the die 30 times, and then we find the average of those 30 rolls, right? So then we do this 200 times. So you're going to get 200 X bars, where for each X bar was based on 30 rolls, right? And then we obtain this distribution. If you look at it, and if you notice, this is much, much closer to an exactly bell-shaped distribution, right? And once the sample size got all the way up to 30, now the mean for this one, for this generating sample that I did, I got 3.502. And the standard deviation of these X bars ended up being 0.312. So what is the main result we're seeing here is that even though our original distribution was uniform, right, for the individual values, in this case of the face of the die, once we started looking at samples and looking at the average of those samples, the shape started changing. It went from uniform to then being normally distributed, right, having a bell curve. The mean, notice that is still at around 3.5, but the standard deviation did change dramatically. It went from a 1.7 to down to 0.312. So it went down dramatically. So that means that the variability decreased, got smaller. So here's the overall result. So what role does the sample size n play in the shape of the sampling distribution of the sample mean? So as the shape n, this case, increases, the shape of the sampling distribution for the sample mean, that means for those X bars, right, for the X bars, it became more normal. And what happened to the spread, right? Well, as the sample size n also increased, so increases, the standard deviation of the sampling distribution for X bar, so now it's about the standard deviation, it became more, it became smaller, right? So it becomes smaller. So this overall result that we saw happening is what's called the central limit theorem. So the central limit theorem says that if you have some random variable x with whatever population mean and whatever standard deviation, in this case regardless of shape, right, then as the sample size increases, then the sampling distribution will become normal, right? So here's the main result, I think, simply stated. For any population, regardless of shape, as the sample size increases, the shape of the sampling distribution of the sample mean X bar will become more normal. And so that's the overall result that we see here. And so that means that for the sampling distribution of X bar, we will also have a normal curve, as we saw back in chapter 7. And so to find probabilities under a normal curve, we are going to continue using the normal CDF. I'm going to stop right here, and then I'll come back and go to the next part.